Hello, welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video we continue looking at our implementation of our binary search tree, and at least the implementation of using it as a map. Previously we had written the get operation, and we had written the append operation, or adding to it. It's not really an append because it doesn't necessarily go at the end. It goes wherever it belongs in the tree. And we had also written some tests for this, and so let's go ahead and pull up that code, and we found that the two functions that we had written work, at least as far as this testing goes, that we can add things and we can get them. That leaves us with two functions left to write. We have a function to remove things, and we have an iterator. And in this video, I generally like to write my functions kind of in order of complexity. While it might be tempting to think that the removing is the next easiest, in many ways conceptually it might be. Code-wise, turns out the iterator is easier. Now, easier code-wise, harder conceptually though. So an iterator is supposed to give us back an object that can walk through everything in our collection. And if we go to like our mutable DLL and we look at the iterator for it, you might remember what it did. It created a rover that started at the head of the list, and because this was our doubly linked list, that was the sentinel's next. And then it has two methods, a next and a has next. Has next, it keeps going as long as the rover hasn't wrapped back around to the sentinel. And next remembers the data at rover and then moves on to the next one and returns that data. Okay. Now in the case of a linked list, it's very obvious what the traversal should do. It should move from the front to the back in order through the list. It's much less obvious what should happen here. In fact, we've already talked about several ways that you can traverse a tree. We looked at the fact there's a pre-order, a post-order, and there is an in-order. And in the case of a binary search tree, it's the in-order that really makes sense, because it will give you back the elements in sorted order. And since that should be something of a natural ordering, or the ordering you care about things, it's the one that we should provide. Now, writing an in-order traversal for our code would look something like this. Private def in order, and we'll pass in a visit function that takes a type. I don't know what I'd want it to take. No, it doesn't really matter. I'll say it takes an A and a B. No, we'll just say it takes a B. The data, and returns unit. Okay. And the in order doesn't do anything. It just calls visit on everything, not B, K and V. So I'll go with pass in the values for my visitation. I could pass in both a key and a value. It's really not all that significant. I just want to remind you of what the code should look like for this. Because it's in order, we're supposed to go left, then right, and then visit, and I'll make this a recursive function where we pass in, well, let's put a recur in here. Def recur takes a node, we'll call it in, and the in order traversal just calls recur on the root. Now the way an in-order traversal works is first it goes to the left, so we have as long as in is not equal to null, we call recur on in dot left. Then we do our visit of in dot value, and then we do the recursion on in dot right. And so this would give us an in-order traversal here. Now, the thing is, this does the visitation of everything all at once. Okay? And that's not what our iterator is supposed to do. Our iterator is supposed to have a next and a has next method. So it's supposed to be able to do these things kind of one at a time. And that's a little bit problematic. This recursive approach isn't going to work for that. Now, kind of a really weak way of doing this would be inside of here we create like a mutable buffer, and we call the in order and our visitation appends to the buffer, and then we put everything in the buffer and we just return the iterator for the buffer. It's a horrible way to do this. But we could write code, it's just that's very memory inefficient because we're literally duplicating our entire collection, all the references to it, inside of this buffer and doing a lot of work to create an iterator. And we don't want to do that. Okay, so how can we do it instead? Well, the way to do this is to remember that what recursion is fundamentally doing. The recursion is remembering where it is in the tree. So this remembers that it's at the 5 and then recursively calls on the 3. And it remembers the 3 and it recursively calls on the 2. And we have the call stack remembering these things. Technically the 2 calls on the null, which doesn't do anything, and then it pops back up and it calls the visit. And it's that call stack that's remembering the work that needs to be done. So when I implement this in an iterator, instead of using the implicit call stack that comes from a recursive method, I am going to explicitly use a stack. So I'm going to put inside of here a stack, which will be a new array stack of node. And so I'm going to use the array stack that we've written previously. And now what needs to happen? Well, obviously, all I can do with my stack is I can push things on and I can pop things off. The first thing that I take off of here is supposed to be this 2. So I somehow need to get, but when I take off the 2, I need to remember the things that are above it in the tree so that I can go back to them, because that's what the call stack is supposed to do. It's supposed to remember those things that we need to go back to. So I want to write a little helper method here. I'm going to def a method, and it's going to be called push all left. And we pass it a node in. We could write this recursively or using a while loop. I'm going to write it recursively because it's a little bit simpler that way. If n is not equal to null, then I want to do two things. Stack dot push of n and push all left of n dot left. So after I build my stack, I'm going to go ahead and call this push all left on the root. And let's look at what that would do. Okay. So when we first build our iterator, I call push all left and I pass it this 5. And because this is not null, it pushes the 5 onto the stack, and then it recursively calls on the 3, which gets pushed on the stack, and recursively calls on the 2, which gets pushed on the stack. It calls with the null when it says, oh, we're null, we're done, and this returns back up. Okay. Note, I could also do this with a while loop. I'm not using the branching. Scala will optimize this because it's a tail recursive function and make it just as fast as a while loop. So it really doesn't matter. I think the recursive version is just a little bit slower, or is a little bit shorter and easier to understand. It also allows me to not use any vars. So this will, our stack will then have 2, 3, and 5. And the 2 is at the top of the stack. So it'll be the first thing that I pop off. And indeed, if I call next, the 2 is supposed to be the first thing that I get. Now, has next is actually a fairly easy thing to write. We have a next as long as our stack is not empty. And because our array stack only has an is empty, I say not stack is empty. And so as long as it's not empty, we have things to take off of the stack. What about next? Well, now next is supposed to, just so we don't forget this, is supposed to return a tuple of key value pairs here. And what I need to do is I need to pop off my stack. So let's go ahead and val ret equals stack dot pop. Okay, so we're going to pop off the value of the stack, and then I want to return the tuple that is ret.key and ret.value. So that's my return value. And at this point, the code compiles, but if I were to run this when I would do the iterator, it would push on 5, 3, 2, then it would pop 2, 3, 5, which is part of what I wanted from the iterator. But we need to do a little bit more. So I left this blank line in here because there's something that needs to happen right there. After I pop off the 2, well, there's no more work that needs to happen. After I pop off the 3, I have to push the 4. Okay. What about after I pop off the 5? Well, then I need both of these, and it turns out that I need to push the 7 and the 6. As a general rule, every time that I pop something off, I need to push onto the stack go to the right, and then push everything down the left, which is exactly that function that we wrote. We're going to call push all left on the right child of red. If there's nothing there, as is the case with 2, it will not pass the if and immediately return. But if there is something there, it will go onto the stack and will run all the way down. So we can kind of follow what this does. Our stack pushes 5, 3, 2. We pop the 2 and return it and don't push anything on. We pop the 3 and push the 4. Then we pop the 4 and don't push anything new. Then we pop the 5 and push the 7 and the 6. We pop the 6 and don't push anything new. We pop the 7 and push the 8, and then we pop the 8, which is exactly what we wanted our iterator to do, is that it gives us these values back, 2, 3, 4, 5, 6, 7, 8, in order that we want them. At least that's the argument here for this code. We don't know for certain until we test it. Def iterator. And go with iterator 7. Sure. So let's say that I add these things in the same order that I had them here, okay, which does produce the tree that we have in that picture. And what should happen for this is that when I run through the iterator, I should get things back in the order 2, 3, 4, 5, 6, 7, 8. So that can nicely be expressed as a range for I in 2 to 8. And let's go ahead, val iter equals map dot iterator, assert equals, the thing that I'm expecting it to be is I iter dot next, and assert false iter dot as next. I guess I could up here assert true iter dot as next. And if we run this as a test, make sure everything saves first. Launching. Uh-oh, we have an error, which is why we run tests. Iterator. So the iterator 7, that's not in code that we wrote. What was this assertion error? Oh, duh. That makes sense. I arrow I. It's good when you screw up your tests and then it says that you were wrong. It implies that your test is actually testing something. So there we go. Because remember, the iterator iterates over the tuples, and our tuple happens to be just int. And there we go. So we have a working iterator, and now we only have one function left to write, and we'll work on that in the next video.